May 17, 1943. Early morning. Albert Speer steps out of his car on a hillside above the Möhne Valley and stops walking. The dam is gone. Not damaged. Gone. A breach 76 meters wide has opened in the wall, and below it the valley looks as if a giant hand has dragged its fingers across the earth. Roads ripped from their foundations. Bridges torn apart. Railway lines twisted into shapes that no longer resemble track. 130 million tons of water came through that gap in the dark, and it has left behind a landscape Speer will describe in terms usually reserved for earthquakes. He is the Reich Minister of Armaments. He has been driven through the night from Berlin because what his subordinates told him on the telephone did not sound possible. Standing on that hillside, he will write one sentence that captures what the British had done. Employing just a few bombers, they came close to a success which would have been greater than anything they had achieved hitherto, with a commitment of thousands of bombers. But Speer is not only looking at the damage, he is looking at the torpedo nets. Still there. Still intact. Still stretched across the reservoir exactly where German engineers placed them. The nets have not been torn or breached. They have simply been made irrelevant. The bomb went over them. It bounced across the surface of the water, cleared the nets as if they did not exist, struck the dam face, and crawled down the masonry to detonate 30 feet below the waterline. Within days, German engineers would recover one of those bombs completely intact from a crashed British aircraft. They would take it apart, examine every component, and attempt to build their own version. They would fail. The question of why they failed is not a story about engineering. It is a story about what a weapon actually is. The man who built the bomb was not a weapons designer. Barnes Wallis was a structural engineer. He had trained in marine engineering, taken his degree through the University of London External Programme in 1922, and spent the interwar years at Vickers Armstrong's designing airships and aircraft. His great achievement before the war was something called geodetic construction, a lattice framework of aluminium so resilient that a Wellington bomber built with it could absorb catastrophic battle damage and still fly home. Other manufacturers could not replicate geodetic construction easily. It was the product of one man's particular habit of mind, a way of solving problems through patient, repetitive, hands-on testing that could not be transferred by handing someone a blueprint. Remember that. It is the reason this story ends the way it does. When the war began, Wallis became fixated on a single strategic insight. Germany's industrial power depended on the great dams of the Ruhr Valley. The Möhne, the Eder, the Sorpe. These reservoirs supplied the water and the hydroelectric power that drove the steel mills and the munitions factories. If you could break the dams, you could paralyze the heart of the German war economy. The problem was that breaking a dam required a force that no existing weapon could deliver. A conventional bomb would need to weigh 10 tons and fall from 40,000 feet. No aircraft could carry that load to that altitude. And the Germans, understanding the vulnerability, had strung steel torpedo nets beneath the surface of each reservoir. Anything dropped from the air that tried to reach the dam wall underwater would be caught long before it arrived. Wallis asked a question that nobody else was asking. What if the bomb never went underwater at all until it reached the dam? What if it bounced? He began with marbles. In his garden in Effingham, Surrey, he fired marbles from a catapult across a washtub of water, watching the angles, the speeds, and the behavior on impact. He realized that if a cylindrical bomb could be made to spin backwards at high speed before release, the backspin would cause it to skip across the surface like a stone on a pond. It would clear the nets entirely. And when it struck the dam face, residual backspin would grip the masonry and drag the bomb downward to a depth where water pressure would amplify the detonation against the wall. Elegant. Counterintuitive. And the Air Ministry's response was immediate and dismissive. Air Chief Marshal Arthur Harris, head of Bomber Command, called the scheme tripe of the wildest description. Within Vickers, Wallis was told he was causing trouble with his silly nonsense about the dams. He was forbidden from continuing the work. He offered his resignation. He did not stop. At the National Physical Laboratory, he ran model tests. In Wales, at a disused dam called Nanty Grow, he proved the core physics. On July 24, 1942, A 279-pound charge placed in contact with the dam wall and detonated underwater blew the structure apart. The principle held. You did not need 10 tons. You needed the right amount of explosive in the right place at the right depth. The question became delivery. Through the winter of 1942 and into the spring of 1943, Wallis ran airdrop trials at Chesil Beach and later at Reculver. Prototype after prototype failed. Casings shattered on the water. Bombs sank short. Trajectories went wild. Each failure refined something. He changed the shape from a sphere to a bare cylinder. He adjusted the spin rate. He narrowed the release height. By April 1943, the weapon existed as a set of numbers so tightly bound together that changing any one of them broke everything. 500 revolutions per minute of backspin, release height of exactly 60 feet, aircraft speed of 232 miles per hour, distance from the dam roughly 450 yards, detonation depth of 30 feet. Standard barometric altimeters could not hold 60 feet precisely enough, so 2 spotlights were mounted beneath each Lancaster, angled to converge into a single oval on the water at the correct altitude. Range was measured with a wooden hand sight built around 2 nails that lined up with the dam towers at the right distance. The change from topspin to backspin came from Vickers designer George Edwards, who recognized the principle from his days as a cricketer. On May 13, 1943, a live bomb dropped 5 miles off. Broadstairs bounced 7 times over 800 yards, sank, and detonated. The weapon worked. 3 days later, 19 modified Lancasters of 617 Squadron lifted off from RAF Scampton. Their commander was 24-year-old Wing Commander Guy Gibson, who had already flown more than 170 operational sorties. Air Vice Marshal Ralph Cochrane, commanding 5 Group, had recruited him with a question that was not really a question. Would he fly one more trip? For weeks, the crews had trained over English reservoirs at night, holding their Lancasters at 60 feet in darkness, learning to trust the converging spotlights. They crossed the North Sea in 3 waves. At the Möhne, Gibson went in first. He dropped his bomb, then turned and flew back across the dam at low level, deliberately drawing anti-aircraft fire so the crews behind him could make their runs. Flight Lieutenant John Hopgood's Lancaster was hit on approach and caught in the blast of its own weapon. After 5 attacks, the Möhne wall gave way. Gibson led the remaining aircraft to the Eder, undefended but wrapped in valley fog and requiring a near-vertical dive over a hilltop castle. The Eder broke just before 2 in the morning. 8 Lancasters did not return. 53 aircrew were killed. 13 were Canadian. On the ground below the Möhne, the floodwater killed at least 1,650 people. More than 1,000 of them were foreign forced labourers, many of them, Soviet women, held in a camp directly in the path of the flood. That is part of this history, and it belongs in the telling. Every like on this video helps keep stories like this one in front of the people who believe the history should be told complete, not just the parts that are comfortable. In the days after the raid, a Luftwaffe bomb disposal officer named Heinz Schweizer recovered a complete, undamaged bouncing bomb from the wreckage of Flight Lieutenant Barlow's Lancaster. Barlow's aircraft had struck power lines near the town of Rees and crashed on land before its hydrostatic fuses could arm. The Germans now possessed the weapon intact. They could see the steel cylinder. They could examine the Torpex explosive filling. They could study the hydrostatic pistols designed to trigger at 30 feet. What they could not see, because it was not a physical component, was the backspin. German engineers launched a program codenamed Kurt. They reproduced the cylinder and dropped it from a Focke Wulf 190. Without backspin, the bomb left the aircraft at the same speed as the plane and bounced unpredictably back upward toward it. The test was dangerous to the pilot and useless as a weapon. Engineers attempted to solve the trajectory problem by attaching a rocket motor to the bomb, meant to break away on water impact. The rocket cluster would not separate cleanly. The program was abandoned in 1944. The Germans had been looking at the answer without recognizing it. Backspin was not a feature of the bouncing bomb. Backspin was the bouncing bomb. It stabilized the cylinder gyroscopically so it struck the water flat on every skip. It slowed the weapon relative to the aircraft, so the crew survived their own attack. And when the bomb reached the dam, residual rotation pressed it against the face and walked it down the masonry to the fuse depth, keeping it in contact with the stone instead of drifting into open water. Remove the spin, and you did not get a worse version of the weapon. You got a steel drum that endangered your own pilot. That is the answer to the question Speer's engineers could not resolve. The bouncing bomb could not be copied because the bomb was not the weapon was the process. It was a year of failed drops and broken prototypes, and one stubborn man adjusting variables until an interlocking chain of precise numbers fell into place, each value discovered only through the failure of the one before it. The marbles in the washtub, the ruined dam in Wales, the shattered casings at Chesil Beach, the cricketer who understood what spin could do to a moving object, the spotlights converging at 60 feet, the wooden sight with 2 nails. Hand the enemy the finished cylinder, and you gave them nothing, because the cylinder without the knowledge behind it was just a container. There was a further dimension the Germans could not overcome. Even a working copy would have had no strategic purpose. Britain's reservoirs were not the single industrial bottleneck that the Ruhr dams represented for Germany. The Luftwaffe had no heavy bomber capable of carrying a 9,000-pound weapon at 60 feet in a straight, slow, moonlit run. And by 1943 they no longer held air superiority over the British Isles. Speer mobilized 7,000 workers from the Atlantic Wall construction sites and had the Möhne rebuilt by September 1943. Wallis protested that a few conventional raids on the repair works would have prevented the restoration. Bomber Command never carried them out. But those 7,000 labourers were not building coastal defences in Normandy during the months that mattered most, and when Allied troops landed the following June, the gaps in the Atlantic Wall told their own quiet story. Harris, the man who had dismissed the bouncing bomb as tripe, changed his mind overnight. The day after the raid, he told Wallis that he had not believed a single word of it, but now Wallis could sell him a pink elephant. That conversion mattered. It cleared the path for Wallis to design the 12,000-pound tall boy and the 22,000-pound Grand Slam deep penetration earthquake bombs that 617 Squadron carried against targets conventional bombing could not destroy. They sank the battleship Tirpitz. They breached the Dortmund Ems Canal. They collapsed the Bielefeld Viaduct. The squadron assembled for a single night over the Ruhr became the most decorated unit in Bomber Command. Gibson received the Victoria Cross. On September 19, 1944, his Mosquito crashed at Steenbergen in the Netherlands. He was 26. Speer, in his memoir, offered the most striking reflection. He noted that just weeks before the raid he had proposed to Hitler that a specialist committee identify the critical weak points in Soviet war production. 4 weeks later, as he wrote, the first attempt was made, not by Germany, but by the British Air Force, to influence the course of the war by destroying a single nerve centre of the enemy's economy. Germany had grasped the theory. Britain had executed it, with a weapon Germany could disassemble on a workbench and still never reproduce. Barnes Wallis was real. Guy Gibson was real. The 53 men who did not come home were real. Heinz Schweizer, the man who pulled an intact bomb from the wreckage and handed German engineering a puzzle it could not solve, was real. And the forced labourers who died in the flood they had no part in causing were real. The bomb that skipped across the Möhne Reservoir on a May night in 1943 was never a machine. It was the visible end of an invisible chain of knowledge, forged through a year of quiet, persistent failure by people who refused to accept that the problem could not be solved. Copy the object, and you copy nothing. The secret was in the years of getting it wrong. If this gave you something to think about, subscribe. These investigations will keep coming. And the stories worth telling are almost always the ones where the thing that mattered most was the thing you could not see by taking it apart.